In chapter 11, we started talking about data mining techniques. And data mining techniques is a process of applying analytical techniques to find some hidden structures or patterns and relationships between or among the data. And data mining is categorized in two big categories: supervised data mining or unsupervised data mining. In the supervised, sometimes we call it predictive or directed. For the unsupervised, we call it descriptive or undirected. In this chapter, we are going to focus on the unsupervised data mining techniques. And we will be discussing mainly two big techniques. The first one we call it cluster analysis, and the other one is the association rule analysis. So the unsupervised data mining depends on the way they learn about the data. If you remember, the supervised data mining or the supervised learning, it's more commonly used for developing predictive models. And the two big primary techniques that we used in the supervised data mining is the classification and the prediction. And these models are used to predict the outcome of the response variable. So we have a response variable and we have predictor variables. So to predict the outcome of the response variable based on many predictor variables. In some supervised techniques, such as regression, the regression is a mathematical model that relates the outcome of the response variable, which is the y, to one or more predictor variable or variables, which is the x's, is estimated. A regression model, for instance, is trained or supervised because the known values of the response variables are used to build model in the training set, because we know the value of the response variable, and this is used to build the training set. Also, the performance of the model is evaluated based on the extent to which the predicted values deviate from the actual values of the response variable in the validation dataset. For this chapter, we are focusing on unsupervised data mining. What makes it special? That it requires no knowledge of the response variable. So that's why we call it unsupervised. The algorithms allow the computer to identify the complex relationships and patterns without any specific guidance from the analyst. So you do nothing. It's an important part of exploratory data analysis because it makes no distinction between the response variable and the predictor variables. All of the variables are the same. So all of the variables, they're going to take values like x's, x1, x2, x3, up to xk, let's say. And there are many machine learning algorithms to implement the unsupervised data mining techniques, but we are going to focus on two of them: cluster analysis and association rule analysis. So as we can see that in the supervised learning, we have the response here. We don't have the response. For the supervised, it's used for prediction. This one are used for the analysis. These are some of the techniques that we use already. These are some of the ones that we are going to use. And we know number of the classes for the supervised. Here we don't know number of the classes. This is the way that we categorize the data. We separate them. However, here we're clustering them. And this is something we are going to talk about. Let's start just looking for the introductory case. We have a student and she's an entrepreneur as well. And she has a vending machine business. And she would like to learn more about the products that she puts in that vending machines. So she wants to have a better selection of candy bars and group them and display them in a vending machine. And this is a good example. So she wants to do the following tasks. She would like to analyze the nutritional fact data, group candy products according to their nutritional content. So grouping. So we have a grouping here. Also, she would like to select a variety of candy bars from each group. We have a selection here. So we're going to select from each group to better meet the taste of today's customers. Also, she would like to display the candy bars in vending machines according to the grouping. So we have three kind of tasks here. what is the best way of doing grouping and selection and displaying, right? And if you notice here, we do not have any kind of response variable. It's all kind of features like calories, fats, protein, carbs, brands. So all of these variables are kind of just variables, right? So as we said, the unsupervised data mining requires no knowledge of the target variable. And as we said, the algorithm use or allow the computer to identify the complex processes and patterns without any specific guidance from the analyst. And we do not distinguish between Y and X. We don't have target variable. And we will be talking about two techniques, the cluster analysis and association analysis. Also, we would like to talk about something. If you remember, we talked about, in one of the chapters, we talked about similarity measures. Similarity measures to gauge whether a group of observations are similar or dissimilar to one another. And if you remember, we used Euclidean and Manhattan distance measures for numerical analysis or for numerical variables. And what we did, we standardized the data and we normalized the data to make them independent of their measurement scales. Also, we used matching and Jacquard's coefficients to measure similarity for categorical variables. We have Jacquard's and matching as well. So these measures are very necessary here. They're very important for both supervised and unsupervised data mining techniques. For instance, in the clustering analysis, similarity measures are used to form clusters in such a way that observations are similar within a group but dissimilar across the groups. So the main idea we are going to use is the distances between the observations that group the data. So we are going to use these measures in this chapter. Because grouping is important, cluster analysis is one of the most important unsupervised data mining technique. What does a clustering analysis do? It groups observation in a data set such that the observations are similar within a cluster and dissimilar across clusters, using similarity measures we talked about. Also, cluster analysis performs useful analysis by summarizing a large number of observations in a data set into small number of homogeneous clusters. And the cluster characteristics or profile help us to describe the different groups of observations that exist in the data. While the cluster analysis can be done or performed on its own, it's sometimes performed prior to supervised learning techniques to help separate observations that display very different patterns. For example, pricey luxury vehicles may require a very different model from the one that is used to price economy vehicles. Therefore, it's reasonable to cluster different types of vehicles into different groups and develop pricing models for each group separately to achieve better predictive performance. For cluster analysis, we're going to talk about two clustering techniques: hierarchical clustering and k-means clustering. So, cluster analysis allows us to form groups of people, products, business transactions, and many other types of observations into internally homogeneous groups where each group has unique characteristics and can be treated differently from the other groups. A popular application of a cluster analysis is called customer or market segmentation, where companies analyze a large amount of customer-related demographics and behavioral data and group the customers into different market segments. For example, a credit card company might group customers into those who pay off their account balance every month versus who carry a monthly balance. And within these two customer segments, group them further according to their spending habits. So the company would likely target each of the customer segments with different promotion and advertising campaigns or design different financial products for each group. Similarly, insurance companies might want to group motor insurance policyholders based on their characteristics such as age, annual miles driven, and average claim cost, thus allowing them to set optimal insurance premiums for each group. Cluster analysis is also widely used in non-business applications. For example, social scientists, public health officials use data on food consumption, physical activities and social demographics variables to identify subgroups of individuals who might be at risk of physical or mental illness. The first type of cluster analysis is hierarchical clustering. Hierarchical clustering, because we said we have two of them, the other one is the k-means clustering. So in this section, in this part, we're going to talk about the hierarchical clustering. Hierarchical clustering is a technique that uses an iterative process to group observation into a hierarchy of clusters. Common strategies for hierarchical clustering follow one of the two methods. Agglomerative clustering, this is number one, or agglomerative nesting, or AGNES, or divisive clustering, or divisive analysis, or DIANA. What is the difference between the two? As you can see from the chart, that the agglomerative starts with each observation being its own cluster, with the algorithm iteratively merging clusters that are similar to each other as one moves up to the hierarchy. Eventually, all observations are merged into one big cluster at the top of the hierarchy. So that's why we call it bottom-up approach. This is the bottom-up approach. Conversely, the divisive approach starts by assigning all observations to one cluster, with the algorithm iteratively separating the most dissimilar observations as one move down the hierarchy. The process continues until each observation becomes its own cluster. That's why we call it top-down approach. Top-down approach. In this section, we will be focusing on agglomerative technique. It's more commonly used approach between the two of them. Sometimes we are going to have data that we have only numerical or categorical variables. Sometimes we are going to have data that have mixed variables, and we are going to focus on this part when you have a mixed variables, because this is the normal situation when you have a mixed variables. In agglomerative, each observation in the data initially forms its own cluster. The algorithm then merges these clusters into larger clusters based on the similarity until all observations are merged into one final clusters, and this final cluster referred as a root. And we measure the similarity and dissimilarity of the observations using Euclidean distance or Manhattan distance measures for the numerical variable, and using the z-score standardization to make the data independent of the scale. What about if the data is categorical? If the data is categorical, we use matching or Jacquard's coefficients. And the choice of similarity measures should depend on the context of the problem. In situations where the non-existence of attributes is poor indicator of similarity, Jacquard's coefficient is preferred over the matching. So this is the way that we are using the techniques in agglomerative algorithm. But the question is what? The question is, if you measure the distance between the observations to create clusters, we also need to find the distance between an observation and a cluster, or between the clusters. Why? Because to make less clusters, because if you create the first clusters, how you merge the clusters based on the distance between the clusters, right? So in this case, we use different techniques. We use a different algorithm. Suppose we have two clusters here, and we think to merge these two clusters. Maybe we have another cluster here, another cluster here. So what is the criteria that we are going to use to merge two clusters? So we either use one of these methods. We use the single linkage method, or we use the complete linkage method, or centroid method, or average linkage method, or Ward's method. What is the single method? The single method, as you can see, is the nearest distance between a pair of observations not in the same cluster. It's the nearest distance, the single. For the complete is the opposite way around, is the farthest distance between a pair of observations not in the same cluster. And the average, or the centroid, the centroid is the center. is the center. Distance between clusters where the mean of values of individual variables in the cluster represent the center. And the average uses the distance between all possible pairs of observation that do not belong to the same cluster. For the word, we use something called ESS, which is the error sum of the squares, which is the square difference between individual observations and the cluster means, measures the loss of information that occurs when observations are clustered. To represent the agglomerative, we use something called dendrogram. A dendrogram, so when you finish the process, we have to visually represent them like a tree, where each observation can be thought of as a leaf on the tree. And this tree-like structure, we call it a dendrogram. And it allows users to visually inspect the clustering results and the appropriate number of clusters in the data. Determining the right number of clusters is somehow subjective, but we can visually inspect a dendrogram to help guide our decision. Let's look at a dendrogram and explain more. Viewing from the top of the dendrogram, we can see the two main branches. Each branch represents a possible cluster of observations. Collectively, the two branches consist of 10 sub-branches or sub-clusters. If you count them, the total are 10, labeled by the values below the horizontal axis. You can see them. The smaller branch on the right-hand side includes 3 sub-branches. They have numbers 3, 8, and 10. And the height of each sub-branch indicates the distance or how dissimilar it is from the other sub-branch with which it's merged. So the greater the height, the more distinctive the cluster is from the other cluster. For example, if you look at subclusters 4 and 5 are very similar to each other, and therefore they are connected to each other at a smaller distance of about less than 3. Because look, the y-axis represents the distance, by the way. While the subclusters, let's say 6 and 7, need to be merged at a larger distance of about, let's say, 6. As a result, we can often determine an appropriate number of clusters by visually inspecting the dendrogram. When a large distance to merge subclusters is detected, it suggests the presence of distinctive clusters. Here, for example, we might decide that the observation should be grouped into 2 clusters only, as the 2 subclusters need to merge at a large distance, about, let's say, 18. So what we do, we cut the tree horizontally, as we do here, to obtain the 2 main branches, the 2 clusters. So if you cut the tree from here, you can tell me what are the 2 clusters that you're going to have. This cluster and this cluster. We can't only rely on the height of the dendrogram tree, because this may lead to a statistically distinctive cluster that have little or no practical meaning. That's why we rely on 2 things: the quantitative measures, the distances, and the practical consideration to determine an appropriate number of clusters. For example, this one represents the process of clustering customers into groups that are internally homogeneous. If a firm wants to target each group for one of the 4 different products that it produces, then settling on 4 clusters seem to be appropriate. 4 clusters, because the focus is just 4 groups or the four products. So the tree would be cut at the green line, as we see. We should also review the profile for each cluster using descriptive statistics. For instance, if age, sex, income, educational attainment, and number of hours online per week are the variables used in the cluster analysis to group customers, each resulting customers can be described with respect to its most defining characteristics. One cluster may include predominantly high income, the other one highly, or maybe the first one, high income and highly educated female customers between ages 35 to 45. Maybe another cluster may include dominantly customers between ages 18 and 25 who spends over 20 hours online weekly, etc. So we can label them like the first one to be labeled middle-aged female professionals, and the second one may be to be labeled as young internet surfers, right? Another common approach to profile clusters is to incorporate variables that are not used in clustering but of interest to the decision maker. For example, we may find that a larger percentage of the customers in the first cluster have purchased our products at least 5 times during the past year, while the majority of customers in the second cluster have not placed any order in the last 6 months. So based on these insights gained from the cluster analysis, the company may design different product offerings or marketing messages to target different customers groups. As we said, data can be only numeric, categorical, or mixed data. Mixed data are quite often of interest in business applications, and to measure the distance between the two observations with a mixed data, we use something called Gower's coefficient. Gower's coefficient converts the value of each variable into 0-1 scale and calculates a weighted average of the scale distances as a measure of similarity between the two observations. The main appeal of the hierarchical clustering is that it does not require the pre-specification of the number of clusters, and it's purely data-driven. It's also easy to understand and interpret. Also, note that because hierarchical clustering evaluates individual observations in order to merge or split them in each iteration, it's inherently slow and does not scale efficiently to a large data set. This poses a major challenge when dealing with big data. So this method is not stable in that the interpretation may change with even a small change in the sample data. And to overcome these limitations, we come up with another efficient technique called K-means clustering technique, and this will be discussed in the next recording.